All right. Hello everyone. So it's time for the final lecture of part 7D. Mostly gain bandwidth product, but we'll also go through the CS amplifiers frequency response, which should be almost exactly the same as the frequency response of the CE amplifier, quite frankly. So let's see, no? All right. So common source amplifier, we had these parasitics, no? CGD, which should kind of look similar to a CMU, right? A CGS, which kind of looks similar to a CPI, which we've also discussed last lecture, no? We also have a CL, well, a CL, which is um, a drain to ground resistance, but well, a drain to source resistance, but could also be, well, we put here as an external amplifier with with an that contributes an output pole, if you remember, no? So here, no, solving for the overall gain, we get that A0, no, is actually still GM are out, no? Or rather, well, the DC gain, AB, would be negative GMR out, no? Finactor out natin siya to get an A0 that's only positive, which is GMR out, our low frequency gain dun sa magnitude response, no? So we also find 1 minus S times CGD over GM, no? Which is, if you remember, no? This also appeared when we analyzed a Miller cap, right? So you can see now a Miller cap would always contribute a zero like this, right? And then also we find a pole term, no? With a pole that's 1 over R out CL plus CGD, no? So here we have the regular pole contribution of just the CL, no? So if we only had this CL as a capacitor, it would only contribute R out CL, right? Kaso, since we have this Miller cap, no, it basically is equivalent, no? So reiterating our lesson last week, it's basically equivalent to putting a CGD here and the 1 minus gain CGD here, no? That's what the Miller effect is, right? So basically, what happened is CGD was referred to that. It increased CL by CGD, and that's what we take, no? So CGD contributes a zero, and it adds a little bit to the load capacitance, no? Not a lot, but a little bit, all right? So this is what that would look like, no? Our zero, again, for reasons discussed in the previous video lecture, the zero would be farther along than the pole. So we start at A0, no, which is GMR out, and then we go down at the pole frequency, which is 1 over R out CL, no? Plus CGD, but typically CL is larger than CGD. All right. Also, for the phase response, no, both the zero and the pole have a 90-degree, a negative 90-degree contribution. We assume that if we assume they're far apart, then this type of step ladder is what would happen. Again, review your Bode plots, 45 degrees per decade, slope 10 degree at a decade before and after the pole and the zero. Now, bakit pababa yung contribution ng zero? Pababa yung contribution ng zero dahil dun sa minus, right? A zero with a plus would have a contribution that's plus 90, no? Instead of a minus 90, it would have a contribution that looks like this, no? But it has a minus, so its phase contribution is negated, no? It's flipped over to be negative instead. All right. So, deriving the input impedance, no? Well, you can easily get this by doing the KCL at the input, no? So, we can get that. You can derive the fact that the input impedance actually becomes 1 minus A through this series of manipulations, no? So we have V in minus V out times S CGD. This is over 1 over S CGD, no? So we send it up there. And by factoring out V in from this equation, we get 1 minus V out over V in, no? Which is the definition of the gain in the first place. So we find V in times 1 minus ASCGD is actually the current passing through CGD, no? So V in over I1 is 1 over S times 1 minus A CGD, which makes our input impedance, actually 1 over S times yung contribution nitong CGS, no? Plus 1 minus A CGD. No, because that's the essentially, no, this is the effective impedance of the CGD, no? So it's since it's the effective impedance of CGD, then basically, since we know this and we know this, no, that's just 1 over SCGS. This is what we didn't know, right? Because of the contribution of V out, no? So through this I1 derivation, no, we find that it's actually just 1 over S 1 minus A CGD, no? If we ignore V out, or rather with the contribution of V out, it effectively becomes S times 1 minus A times CGD, no? So we basically increased that we basically increased CGD, no? It's really just a roundabout way of saying the Miller effect again, no? So, Miller effect, tatanggalin natin to, bababa natin siya dito, times 1 minus A, no? That's what I was saying earlier, right? That's what we saw in the previous lecture as well, right? So, our input impedance essentially compounds into this thing, no? So, it's a pole at 0, no? So it has a pole at 0, which means it's just a permanent minus 20 dB per decade. All right. So for the output impedance naman, it's still the same as before, no? So doing the Miller effect again, we transfer this here, and this becomes a CGD over there. We add that to CL, and we get this, no? So originally, it would have been R out over 1 plus S R out CL, but now we have a plus CGD, no? Because of this, no? So it's a new lens to look at the CE amplifier, the CA amplifier with parasitics and analysis that we did before, right? Discovering the actual contribution of a Miller capacitance allows us to view these analysis in newer ways, no? So, also effective transconductance. This one you can just derive it by taking the KCL at the output side, no? So we have GMV in, R out, and well, GMV in, tapos papasok siya dun sa CGD, no? So ditong dalawa lang yung current mo. Wala to, bakit? Kasi V out is shorted, no? V out is 0. So this is the short circuit output current. So GMV in at saka CGD lang yung meron tayo, no? So we have GMV in, tapos V in, V out minus V in, but V out is 0, no? So minus V in. So in long form, this one would have been V out minus V in SCGD, but wala tayong V out, so it's just a minus V in, no? So arranging that, properly, no, we just factor out GM, basically, send V into the other side. We get GM times 1 minus SCGD over GM. And we find that the 0 in the gain actually appears here in this GM. No, it's the SC mu over GM. No. All right. So finally, we get to the next part of the lecture. No? So actually, the meat of this lecture is the gain bandwidth product. No? And it's pretty short naman. No? The gain bandwidth product is basically the so we find it useful because it's the frequency at which your gain, the gain of your amplifier, no, it's an amplifier, it should amplify your gain. The gain of your amplifier hits 1. At that point, you cease being an amplifier at all. No, this is why this is a frequency of interest. No, so other definitions, before the first pole, we call that the bandwidth of the amplifier. No, it's the band. No, it's a range of frequencies is called the band. It's the band at which you want to use the amplifier. No, that's your bandwidth. No, and before the first pole, that's your bandwidth. No, so assuming a single pole amplifier, though, no, we can have a relationship between the unity gain frequency. No, so basically, unity gain frequency. So the unity gain frequency can be derived for a single pole amplifier, no? So assuming ganito yung form ng system mo, doesn't matter what these are, no? This could be GM R out minus GM over R out 1 plus S CL R out, no? Could be like this. Actually, sige, let's make it more realistic. That's actually RC, no? Kung hindi ideal current source yung source mo, then this is an example, by the way, don't multiply that. So, yan, that's an EG, ganon. So, a single pole amplifier like this, no? So, a single pole, okay. So, a single pole amplifier, no? Example of a single pole amplifier. Let me just draw it, no? So, you have RC. Yan, 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 yan. Tapos, lagay tayo ng CL. Diba? We derived how this works. This one is a single pole amplifier. So look at the previous lecture. If you don't believe me, it's a single pole amplifier. No, this is exactly what I wrote down here. No, so ano naman, no, kung single pole amplifier siya. Well, it turns out, no, that if you try to derive this being equal to 1, meaning unity gain frequency, then it turns out to be like this. No, and then we're going to do some algebraic manipulation in the next slide. So squaring both sides, tapos assuming that this is larger than this, which it tends to be, no? I'm going to say it tends to be. I'm going to show you how it's not going to be. But if this is much larger than this, no? Which is true for the Bode plot, no? It's not true for the actual magnitude plot. You get this, and then you send that to that side, and you get that the unity gain frequency is actually your gain bandwidth product. So this is your bandwidth, right? This is the bandwidth of a single pole amplifier. So the bandwidth of a single pole amplifier times the gain of that single pole amplifier gives you the unity gain frequency. Now, do note this A0 is not in dB. No, it's just A0. This one is 20 log A0. This one is just A0. So yun lang naman, no? That's the gain bandwidth product. It's a way to calculate the unity gain frequency. Right? So, yun nga, no? So, omega P is actually your bandwidth for a single pole amplifier. If you multiply that with the gain, it gives you the unity gain frequency, your gain bandwidth product. No? All right. So, another thing is that actually, it's interesting, no? We multiplied this and that, and somehow, since this is a log-log plot, by the way, this is in log, no? Right? And this is also in log, no? Somehow, when we multiply this and we multiply that, no? We always get the unity gain frequency, no? So, ano nangyari, no? Well, it turns out that anywhere along this 20 dB per decade line, no? If you multiply the this, no? If you multiply the value at x and the value at y, you would always get the x-intercept, no? So that's that. Well, okay, it's not x-intercept, no? It's at 0 dB, no? So it's your unity gain bandwidth. So you would get 1 intercept, no? Not 0, not x-intercept. All right. So paano kung two poles yung system mo, no? So gain bandwidth product is fine for single pole system. So paano kung two pole system? Well, there's a case where the there's a case where pole number 2 is actually greater than the unity gain bandwidth, no? Which means that you are already at the, so 0 dB would be here, no? And you would now have negative dBs down here, right? So you hit the unity gain frequency before you start going down 40 dBs per decade, no? So it doesn't actually affect it, which means that it doesn't actually affect the relationship of omega u versus omega p1, no? So in this case, a uh, omega u is still equal to the gain bandwidth product kasi mas mababa sa the contribution of omega p2 starts after the unity gain frequency, no? Hope that makes sense. Also, I think this figure, no, dapat 20 dB per decade siya, tapos mag-hit ng the omega u, tapos saka pa lang siya bababa ng 40 dB per decade pagdating sa omega p2, no? So I don't know why it starts going down at omega u. All right. So, the other case is when omega p2 actually occurs before omega u. Now, if you try to use the original formula, you would be deriving a unity gain frequency, no? Omega u star, that's wrong, no? Kasi bumaba na, like nagkaroon ng mas steep na decline yung yung magnitude response mo, which means that the unity gain frequency actually occurs much earlier than you think it than the gain bandwidth product shows you it does, no? So ano mangyayari in this case? Magbabago yung formula natin ng gain bandwidth product. So doing the same thing earlier, no? So let's get the magnitude response, which is just the magnitude of the factors of the product of the factors, no? So that's a0, magnitude of a0 is a0, magnitude of this part is 1 plus is Pythagorean theorem of that part, and magnitude of that part is also Pythagorean theorem of that part, no? Let's assume they're all greater than 1. Then you can pass this over to that side, no? So we get this. Now, the interesting thing that happens here is if we take the square root of both sides, no? Okay, so let's take the square root of both sides. You end up with a0, and then you end up with omega u, omega p1, omega p2, no? So you put omega p1 and omega p2 on the other side, but you still have a square on the unity gain frequency. So you take the root of the square, and now you get this, no? So this is your new expression for the unity gain frequency, no? For a two-pole system that has the pole number 2 coming before the unity gain frequency, no? So what can you do for a two-pole system? First, you try the original formula, no? You try a naught times omega p1, no, times the lowest pole, and you get an omega u. If that omega u is less than the other pole, then you are correct, no? But if the omega u that you got from trying that formula is greater than both poles, then you have to use the second formula. no? And that's pretty much it, no? That is the end of the EEE 131 lectures. All right. So, last thing I wanted to mention is the fact na tinanggal natin yung 1 din, no? Tatanggal natin yung 1 with an approximation assumption. And that's because of this, no? We have an assumption to begin with, no? Right? When we make our Bode plots, we have an assumption. We approximate it, no? Kasi in reality, pag ganun yan, di ba? That thing is smooth. It's not steep like, well, it's not sudden like we make it in the lectures, no? Like we make it in Bode plots, no? The actual magnitude response is like that. So, it for your Bode plot, it doesn't matter, right? Kapag malayo si omega u kay omega p, no? So kapag malayo si omega u at si omega p, you can remove the +1, right? Which gives us A naught omega p is the gain bandwidth product. But think about this. Kapag nandito yung drawing natin, then the actual magnitude response is actually very different from the Bode approximation, no? From the piecewise Bode approximation. So then, your calculated gain bandwidth product would be there, but the actual gain bandwidth product would be there because the real magnitude response is actually going down before your assumed piecewise linear plot, no? And that's what this +1 represents, no? Our assumption that removes +1 is the assumption that omega u is far away from omega p. Because if it's not, magiging significant yung drop na yon, the fact that the elbow is not accurate. All right? So with that, ends our lectures for EEE 131, and good luck sa finals.